Okay. So today there are two topics. So we will speak about kernel perceptron algorithm. So I explain what is kernel technique, and we will speak about prediction with expert advice. In the seminar, there will be some repetition of probability theory, some simple exercises. But I think it's not a problem for you, this probability theory. Okay. So um, so we spoke about fitting half spaces. So sometimes half spaces are not enough, not complex enough for finding decision border. And so that is, I take example, just that there is one feature. It can happen that there are pluses here, minus here, and pluses here. So we have 6 points. And so half space here means threshold. I mean, threshold classified as plus on one side, but you understand thresholds on both sides, but also with flipping. And this doesn't work here. But what can we do? We can take all polynomials. We can do polynomial feature augmentation. For example, we can change the feature from x to x squared. And then we will have, so here is x squared. So we will have something like this. So there will be plus here. The minus might be here, for example. And now it becomes easy to separate the negative ones from the plus ones. Well, actually, let us say we can do something like this. So we have now two features. We do polynomial augmentation. So if we have more coordinates, we can take just all monomials of degree 1 and degree 2. So another example where this works, if we have 4 inputs, let's say we have 2 coordinates now in the input. So x equals R2, and we have something like this, a minus here and a minus here. So 4 points in the training set. We cannot fit a half space that separates them. However, if we map x1, if we do x1, x2, if we do augmentation, x1 squared, x1, x2, x2 squared, for example. So now I'm dropping monomials of degree 1. So, but then it becomes separable in this three-dimensional space. Because we just need this coordinate, x1, x2. This will assign this to be negative and the other, oh, sorry. Yeah, I should have more pedagogical would be to flip them like this. Okay. And then just the prediction is the third coordinate. Okay. So what people do in general, that say they map vector x in Rd to a vector consisting of all monomials, but of degree at most some let us say e. But the problem is that this is a huge feature vector. It's very expensive to compute it. And so how many monomials do so what's the dimension of this vector? And so the new vector, if the dimension is d, it will be something like theta d to the power e. So usually e is not too big, like 4 or 5 or something, but still it's a disaster. So yeah. So so problem is that if typically d is huge. It can be in the thousands. In current application, there is so much information about the objects. So that just taking a small power to the power 3, 10,000 to the power 3, it doesn't fit in laptop memory anymore. So we want to avoid this. And so here comes the trick. What we will do is we will make an algorithm that does not depend on the feature vector, but only on dot products of feature vector. So we rewrite our algorithm so it only depends on dot products and then find a way to compute dot products efficiently without evaluating the mapping. So that's our plan. And so we will, and it's a very common trick. And like many algorithms you will learn, especially as VM, it's essential there. This kernel trick can be applied, but also in linear regression, just many places. And in the end of the course, we will show that this kernel technique is used implicitly during the training of neural nets. So there is some connection. So there is implicit theory of why they, when the network is really wide, why it generalizes well. Okay, so just to motivate this technique, but first let us see what's happening with perceptron algorithm. So let's write it, let's remember the algorithm. So perceptron algorithm, first step was that we set WT equal to 0. So we have X equal to RD, Y equal to -1 plus 1. So this is important. And then while true, so receive XD, then predict Y equal to the sign of W times XD. And then there is update, receive the true label or just any label. So in agnostic setting, we don't have such thing like true label. Yes. And then we update. So if YT different from YT hat, the predicted value, then we have WT plus 1 equal to WT plus YT ounce WT plus 1 equals to W. Okay, so this is boring weight because you already knew this. So how can we rewrite this so that we don't need the feature products themselves? And so the plan is just to expand the definition of WT. And so in this algorithm, we can at any moment say that WT is equal to the sum of YIXI for I. So let us consider so I in the set of rounds with wrong prediction. So that WT, okay, there is no space left. And let me win. Okay, I do have a bit of space left. Rounds with wrong prediction. Okay, so then we can just substitute, and we will see that we will be good. Yeah, I need to write something about the prediction. We write prediction. Yeah, but then here we have the prediction. So we just expand this. Sum of I by E by I minus I dot X. So this is our prediction. And what we do here, we just update the set rounds with wrong prediction. So now WE unit else. Okay, so we did something very easy now. So this is just the same algorithm written in a different way. And so here we see how we make predictions on a new input XT. So I'm not writing it separately. Okay, nothing changed, and we reached our goal. And so we don't need the feature vectors. We just need the dot product. Okay. So yes. Now let us think about polynomial augmentation. In the second step, I will convince you that dot products are easy to compute when we expand to all monomials here. So let us first think about quadratic augmentation. So let us consider all monomials and also repeat the ones that are equal up to reordering of all the factors. So these are always the same value, but let's play it for mathematical reason. Let's make okay. So now so this is our mapping phi. And now let us look to phi of x times phi of x unit. This is the dot product. And let us, why not? Let us do it for any dimension.
Sorry, what is x tilde?
Yeah, they're just two inputs.
Oh, okay.
Yeah, I don't want to use subscripts because now we are using indices for coordinates. It will be confusing. So let us say that let's have some dimensions. Let's say that I goes from RD to R capital D. So this is equal to the sum. So and we go from X is mapped to all monomials of degree 2. We let's say exactly 2 for starters, and then with repetition. So a vector. So we will have that D is exactly equal to D squared. Okay. So now let us evaluate dot product. So yeah, I just asked something. We're going slow, but so there is a chance to make everything clear. So we will go over all pairs of indices smaller than D. And we will have here xi, xj. And the second one will be x tilde I, x tilde j. So this is dot product of feature vectors, since every coordinate is monomial. Okay, and this is equal to you can say the sum over I, xi tilde times the sum over j, xj, xj. So it's equal to xi times xj squared. Sorry, x times x tilde squared. So this is for 2 dimensions. We can also do it with for any e dimension. IE. So we will have more sums here. So we will have more indices, E1, I2, and so on. IE smaller than D. Okay, so here you have to expand. So that there are more things here. I1, I X, IE. Okay, you're all clever enough to deal with this. So and then I directly write this. So we have the same thing. Now, what if we want all monomials of degree up to here? So we can have it also in a very similar way. What we just do is augment the vector by first appending a 1 here. And so the 1 will decrease the degree each time we use this 1. And then what will be the dot product here? So what should I write? So let me write it explicitly. So we will add a 1 here. And here we will use, okay. Here we will have x1, x2, and 1 here. So this is the example. I will not write the general definition. You understand the technique. First add a 1 and then do the same thing. Take all E coordinates. And so what will we get here? Just to check that I'm not going too fast. So how will the formula change?
X squared, X tilde squared. Sorry, what formula?
Okay, so now I change the definition of phi E. I take all polynomials, all monomials with repetition, but after adding a 1 to the vector here.
Mm.
Maybe it might change.
Yeah, so there's a small change. Can you say it more clearly?
Just 1 at the end of each vector would appear like something like that.
Yeah. Okay, it's not clear yet. So let me say it more. So here is the example with what we do. So the mapping x1, x2 will first go. What I'm suggesting here is we get x1, x2. Let it first map to x1, x2 with 1 here, and then remember the previous map. So here we have x1 times 1, x1 is actually there was a mistake. We also have the other orders. So we have 1 times x1, 1 times x2, and a 1 here. Like this. So this is the vector that we obtain, where we apply here the previous mapping. Just for a while, we forget that there is a 1 and we think that there is x3. We take all monomials and then the x3 we replace by 1 again. So this is a new mapping. So, okay, let's call it phi E, phi 2 prime. We here applied on 2-dimensional vectors. So when I change this, then we will have something else here, but we pretend that the last coordinate is still a variable. Just in the end, we'll set it equal to 1. So in this step, we will have again vectors. Let's first pretend the last variable is there. So we have plus xe, and then set it to 1. So in this dot product here, there will come a plus 1 here. And then we take to the power e. So nothing changes. Now we can play a little bit with this. And so I'm deriving a polynomial kernel. The question is how much emphasis, how much advantage should be given to polynomials of lower degree. We can play with this. Instead of 1, we can put a constant here. So then, so if we want to say that lower polynomials are more important for the training, so we prefer lower polynomials, we can put a big C here. And then we have big coefficients for the low degree polynomials. And then it will mean that if we apply this feature mapping, So the coefficients of W, so the coefficients so the implicit WT will change faster for the coordinates will change faster for low degree polynomials. So that's when we think they're very important. So that's how we can apply a certain regularization. And the change here, 1 will be changed by c squared. So this is called a polynomial kernel. And the exponent is the degree of the polynomial. And this is our magic. So before, imagine that x has size 10,000, and we want to fit polynomials of degree 3. Then now we can evaluate these dot products very quickly. Just really fraction of a second. Even if your training set is 10,000 points, it will be really quick if you carefully in NumPy and so on. And
Sorry,
yes,
why is there is a square, c squared?
c squared. Well, remember our trick. So what did we do? To x, we appended one coordinate. And then we have the result. So the old result was x times x squared. But now we do an extra step. We first add a coordinate and then pretend it's just a normal coordinate, do everything, and then change back the notation. So, but when we change back the notation,
Okay.
here is a vector, the dot product vector c times, x still is,
Thank you.
yeah, with it needs to be clear, and that gives c squared. So here we also have c squared. Okay. Yes. So then, so we could say, so then when we run the perceptron algorithm, here we're running. So now let us define the polynomial kernel KE. It's a mapping that takes two inputs and it gives a real number to the power E. So now we can use this kernel and rewrite the algorithm. So what's happening in the first step? Here the inputs are replaced by the inputs after applying the method. And so there is only one place where the vectors themselves are needed. And so in our algorithm, we have phi xi times phi xe. So it's still visible. All right, it's still visible. That's making me line. Okay, and now we know that this product can be replaced by the kernel. So I rewrite it again. We have K of xi, Ke of xi, x. That's also how we make prediction. So normally, I forgot to tell you. So what if you have a finite set, a training set, then people run perceptron algorithms several times, or at least Frank Rosenblatt in 1958, I think it was his strategy. So he programmed the computer and run this algorithm. And then he built first digital camera that could take 20 by 20 pixels from the picture. And then he had two types of pictures and he ran this algorithm to learn the linear decision border. And then he wrote in the news that he invented the method that will at one day be the beginning of machines that can think, speak, feel like humans. So yeah, it's quite ambitious to say this with such an algorithm. Now we know more, but actually we can think low of such overextended thought, but precisely the same is happening now. So people on you, if I go to YouTube, of course, then there are all these movies of people saying that, oh, next year there will be machines that think like humans, and so it just happens every whatever 15 years or something, that people think, oh, we're so close now, we're almost there, just a year or something. Okay, sorry, I'm distracted. So what I'm saying is that we can run this kernel algorithm. So, for example, in the seminar, there is exercise where you try to, where the true model is a circle. So there are some inputs that are clearly separated by circles. And then you will say the perceptron will make a certain number of mistakes. It was like 60 mistakes or is the, I don't remember the answer, but it's not too crazy. That's what I want to say. Although there is quite a huge border. I think it was, the inner circle was 2 and the outer circle was a radius 4, and here are all 1 pluses and here are all minuses. So just, it's quite clear. But it's quite easy to fit, but still 60 missed after, or 90. It's your task. Yes. So oh, I'm not finished. We need to say one thing more general about kernels. Okay, so what we did now, we thought about feature vectors. We say, oh, we want to fit, for example, quadratic polynomials. Then we derived kernel and we got a fast evaluation. But nowhere in the algorithm we do need the feature vectors. So people say, let's think about good kernel. We want that similar objects have a high value, random independently random objects, low value. And then this algorithm will make few mistakes, provided such implicit mapping exists. If mapping doesn't exist, in this algorithm, maybe in this algorithm, I didn't think about the question. What happens if you just put random function here, arbitrary function? But another algorithm like SVM, you will get into trouble. There is no guarantee of convergence. Although in practice, you can be lucky. Okay, but now is the question, if we just make a function that's easy to evaluate and is good for application, how can we know that this is a good function? How do we know that we can find such a mapping? So do the reverse. And this mapping can be horrible. People, we will see with Gaussian kernel is infinite dimensional vector space you need for it. But yeah,
Isn't this always the function of the kernel that is written on the board?
so can you repeat the question?
Like, isn't this function always like the one that we use?
So there are thousands of kernels. So for each application, people say this kernel is a good one. Yeah. And so, but you're right, polynomial kernel is popular, but more popular is Gaussian kernel. It's, I can write it. So it is x tilde equal to. Oh, this exponent, I think you can guess it. So it has a hyperparameter sigma squared, and then x minus x tilde squared. So this used like in 20 years ago, SVM was actually beating neural nets, and with this kernel. And so the sigma parameter had to be tuned with cross validation.
Shouldn't there be one and minus one? So exponent of.
Sorry, yeah. Sorry. Yeah, good point. Thank you. Yeah, and we will soon explain why this minus is essential for risk bound. So yeah. Okay. So but to answer your question, so what we're saying is that first, when we spoke about polynomial kernel, we first chose good feature vectors, thinking about application. And then, so we looked at the pictures, we say, oh, squares will help us. And then we went to this nice kernel function. Now we do the opposite. If we think about the question, if we propose a function, can we find a feature mapping?
Okay.
So can we define the phi? And it might be terrible phi, we don't care. Because it's only needed for theory. Okay. And so we will think about this question for finite input spaces now, and then in one of the last lectures, we do for infinite spaces, because it's kind of easy theory. It feels like almost a lecture, but I put it in the end. But for finite, we can just do it in a few minutes. Make a very nice So let us do an example of a bed function first. So let's so let us have x tilde equal to indicator that x is not equal to x tilde. So here, let's say that x is the finite. So recall that kernel is a function of x times x to real numbers. Okay, let's make our life easy. Let's say that x is just 12. Okay, then this function is 2 by 2 matrix. And it's like this, 0, 1, 1, 0. So now I claim that there exists no implicit mapping phi, such that phi x times phi x tilde equals to k x tilde. No phi. Such that. So how do I prove this? So let us look to phi x minus phi x tilde. And let us look to the norm square. This should be at least 0. And so it is equal to phi x squared plus phi x tilde squared plus 2, sorry, minus 2 phi x times phi x tilde. Okay, and now you see the problem, right? Can you finish? So can you evaluate the right-hand side? So we substitute back the kernel function. Here we have the norm of phi. Norm of x, so this is always 0. Same for here. But then if x and x tilde are different, then this is 1. And so if x is different from x tilde, then we have here minus, so it says 0 equals 0 bigger than minus 2. Okay, so we understand no such function exists. Oh,
Let
that
me
is,
have a question. Why does the norm of phi of x equals to 0?
okay, phi of x. So it just, this is Euclidean space. Norm in Euclidean space. So if z is in Euclidean space, the squared norm is equal to z dot z. And so the norm squared is equal to kernel in x comma x.
Oh, thanks.
Yeah. Please ask questions. Um. And so basically, this is the only obstacle. Such this inequality is only the only obstacle that can happen. If we take linear combinations of input mappings, we need to have something semi-definite positive. So now let us go. So I will move this example, and let us say that x is finite. Okay. Then we can associate this function to a matrix. So let's say f is the size is n. And then we can associate this, we can say that x is n by n matrix. And then the following is the theorem says that following are equivalent. What? For all vectors C and Rn, C transpose AC is 0. Two, there exists a mapping that is defined from RD to both ways. Not from RD, but from X to RD. And so that's for all time IG smaller than n, we have Kij is equal to I times phi j. Okay, and here I just say, sorry for changing x all the time. So let's say that x is equal to the natural numbers. Make everything formally correct. So here is the theorem. So these are equivalent. And so either this is called, so this condition for a matrix is called positive semi-defined. Defined. It's the first time you learn about positive semi-defined matrices or
Not sure.
okay, you already know, that's very good. And so either kernel matrix is positive semi-defined or there exists a mapping. Okay, so now our plan is to prove this. So which direction is easier, you think? Just guessing by looking at the form of the statement.
Just from 0 to 1 is easier.
Yeah, from 2 to 1 is easier because if we want to go down, we need to tell what is phi. So let us go to 1 and we already, and I think you can already tell how it goes. And so if we believe 2, why do we get 1? So we will look at the specific vector. Oh. 2, the 2 implies 1. So let us look to the norm. So let us take any C vector. We need to prove that this is true. So let us look to the norm of the vector C1 phi of 1 plus Cn phi of n. And let's look to the squared norm. Okay, do you see what is a squared norm? Did I need to write it? Can you guess?
Like this C transpose KC.
Yeah. So the square norm is precisely this thing.
Why?
Okay, let's write it. So it is equal to C1 phi 1 plus, so I will write it as a dot product first. By n. Dot product. And here the same vector. C1 by 1 plus and so on. So it is equal to we sum over all n here. All so we need two sums. Yeah, it's very good. We need two sums. So we have Ci, Cj, phi I dot phi. I should have used sums from the start. Okay. And now we just replace this by that's equal to Ci K by J Cj. And here we have sum I smaller than n, j smaller than. And then, of course, there's no negative, and we have this inequality. So now we will go, we need to prove that 2 implies 1 implies 3. So for this, I will use a property. So there is, I forgot how it's called, UV decomposition. So we can write any matrix can be written as U diagonal V, and U and V are orthogonal. And so you compute a base for column space. And the V is some base for row space. This is diagonal matrix. And this implies, so if K is symmetric, sorry, I forgot to say that in one, we also have to add the condition that K is symmetric. So if K is symmetric, we can take V equal to U transpose here in the decomposition, because diagonal is for sure symmetric. Okay, what I want to say is if K is symmetric and positive semi-definite, we can write K as B squared or R squared. R is the root of K. And this follows from this decomposition. Because R is equal to this, but the D replaced by square root. So R is symmetric matrix. Okay, and so this R will provide us with the matrix. So we will say that phi of I is equal to the ith column of R.
Can you please explain why K is equal to R squared?
Okay, so I claim that there exists R such that this holds. And we get R by R is equal to U square root of D times U transpose. D is diagonal matrix.
Okay.
So we take square roots on the diagonal. Okay. So now I say that phi is equal to the ith column. Let's use Python notation. Okay, and now we have to check that dot products are equal to the kernel. And this is just, or can do it, some can do it in the head. So let's evaluate phi I dot product phi j. And so it is R. I forgot, it should be an I, of course. So we will take the sum over K of phi I R A J. Okay.
So you can just say that K is R squared, so R times R transpose, so the IJ, AJ, element
Yeah,
would
so
be just,
we can flip the indices because R is symmetric. That's what you're saying. And then we just have, so this is equal to K I J. And this is equal to R product of R transpose. With R transpose is equal to R. Sorry, this is what we want to prove. I'm sorry, I write that. So R transpose is equal to RR is equal to K. IJ, K, IJ. So that's the proof. So dot product equals Kij. And so this is okay. So this is easy condition to check. But it's also important, for example, this condition, when we take the square or multiply two kernels, we get again a kernel, because this condition keeps remaining true. Sorry, product is non-trivial to prove, but if we add two kernels, we have again a new kernel. If we yeah, okay, and so later we will prove about products, and then exponent also preserves kernel. And then we can build more and more, like prove that Gaussian is a kernel. But this is for finite x. For infinite x, we need a bit more. For infinite x, so if the countable dimension, it's okay. But in general, if x is continuous space, we need to replace this by integrals over function c. But then the theorem is still valid. But this is Mercer criteria, and then we need some special mathematics for it. And that's for later. Okay, that's
Sorry.
yes.
The question, why is K symmetric from the first proof? Have we to prove?
Yeah, so well, if this phi exists, then we should have this property, but dot product is symmetric.
Oh.
Yeah.
And do we use, in the second proof, do we use that K is semi-defined positive? Or do we just use that it's symmetric?
In the second proof, yeah, we start from saying that it's positive semi-definite, and we use it when we say that square root exists. If D has negative elements, then yeah.
Sorry, but dot product of matrix is not symmetric.
This is dot product of vectors in Euclidean embedding after feature augmentation.
Mhm.
So so here x2 RD. Okay, so that's it for kernels. So now you know a big secret, easy secret that was very well known 120 years ago, 115 years ago by Mercer, but then became important much later again. Yes, and now I will speak about prediction with expert advice for the last 15 minutes. So I prepared some slides. Good, thank you. Otherwise, it would be problematic for the seminar. Okay. Any questions?
Yeah,
That's not, that very first encounter recently, this sort of technique makes too much mistakes, it will be difficult to compute. Are there any ways to deal with such problem? Like we have the Y predicted equals Y sum. And if we make much mistake, the sum would be consist of too many elements.
So you
Are
want,
there any
I,
ways to
yeah.
deal with that problem?
Yeah, so there is a risk about, so I don't have time to discuss it, but you need to learn it anyway for the homework exercise. So I will skip it, but let's speak. So what happens, your question is, if I understand correctly, your question is what happens to the mistake bound after we apply kernel?
Yeah, like that's, if there are too many mistakes, it will be computation.
Yeah. So let us try it. I will just write the formula for the mistake bound. Okay.
then let me change it for the recording.
So what we said is for every so just in Euclidean space, let's recall what we had. So we have a fixed dimension D, and we said that for every V, for every input sequence x1, y1, x2, y2, and so on. And then the number of mistakes. Wait, I need one more thing. Let R be equal to the maximum norm of an input. Okay. And then perceptron makes so number of mistakes by perceptron.
It's dying.
Perceptron, that is norm of, yeah. Look, it's my last one. Yeah, this one. So we have the norm of V squared, R squared, plus sum over all V, 2 times maximum of 0 and 1 minus E times xi, xt, yt. So that was our mistake bound. Okay, so can we get rid of all norms and dot products after augmentation mapping? So let's plug in everywhere the kernel. I also need to say what is the prediction rule. Well, the prediction rule, I've already written it there. So remember, so there we only use kernels. So, so now how does this, how is it changed? So we will, so what will be V? V will be a prediction rule of the form where we take some tildes. So let us, to get a useful result, let's take some tildes and coefficients. So let us just take any bunch of points and coefficients. And then let's say that our prediction rule after sorry, let us consider a V of the form that's a linear combination of feature mappings like this. So to get rid of a V, let's formulate a prediction rule. F. So F. So the prediction rule depends on the tildes, x tildes and the A vector. And if we give it the test point x, it will be sum of AI, K, x, I tilde, x prime. Here A going up to S. So let's consider a function of this and replace in this result all the norms, all V appearances by this prediction rule. So what will be the risk bound then? Okay. Well, we need something more. Let's calculate the norm of V. So let us define this thing here. It will be the norm obtained from Fy. So for this, well, we compute, remember the formula that was here. It was a linear combination of feature vectors. So what I'm doing here is, I say to predict F, I take a linear combination of feature vectors and take the dot product with the test point. I do the same. So we get the norm in the same way, and the norm will be sum of I, K, X, I tilde, X tilde J, I, J, where we sum over I and J smaller than S. So this will be the norm of F. And now our mistake bound will be R squared. Oh, I need to tell what is R squared. What is the new R squared? Will be the maximum norm of the feature vectors. So it will be KXI, XI. And so here is our input sequence. We will take the maximum value of KXI, XI. This is R squared, and now we are ready. So V squared becomes F squared. Okay, I'm explaining it a bit fast. And then we have the sum. And now we'll try to think what will be this thing. It has a simple form. It will be maximum of 0, 1 minus F x tilde A of X. Okay, so how did I arrive at all this thing? I just choose V. So the proof is very easy. So actually I should have told you right away. I just choose V equal to sum of AI by X tilde I smaller than S. So here I have a result. I formulated a bit messy way, but it's in the lecture notes without using the implicit mapping. But to see why it's true, we just apply this result after applying feature mapping to all x's and choosing V to be this vector. So the question is, can you find special inputs and coefficients so that you have a function that makes good predictions so that this is small, but at the same time, F has small norm, so this is small. And now we can see why Gaussian kernel is so good. Because the kernel is already helping us with keeping R small. So remember, it was exponent -1/2 sigma squared norm of x minus x tilde. So if x equals x tilde, we have 1, and this thing is bounded. So this is why Gaussian kernel is. But okay, I need to change for the last 15 minutes. Now it's last 15 minutes to the slide. So let me first log in. Okay, so now new topic is prediction with expert advice. So what's the problem? So some years ago, I had to organize activities for children, and then 3 days in advance, I have to announce what is the activity, inside or outside. And then 3 days later, it would happen. But if I expect it would rain, then it's important to do it inside. If it's shiny and it's inside, then they're unbearable, and so I make a prediction, and then I receive punishment again, alternatingly, like online prediction model, and then I look to various weather websites, so France, Holland, and so on, and there give different predictions, and I try to figure out which one is more reliable. So, and then my goal is to predict as well as the best website. If you play on the stock market, you look to crazy people on YouTube and try to figure out which one is good in predicting which stocks go up and down.
No.
Oh, no, but now it's easy moment with central banks. Yeah, so let's see when everything goes. Okay. Let's keep it for later without recording. Okay, so yes, so what we have here is there are a game and there are two players. So that's called prediction with expert advice. So the websites, they are experts, and they tell you which label to predict. And there is an opponent. It's called okay. And our task is to aggregate predictions, and it's closely related to agnostic mystic model. And we know that like taking majority vote is a good idea, and we can put weights and so on, and the theory will be very different. But now in this theory, we also are given an extra power. So the labels will always be real numbers, 0, 1, or a number between 0 and 1. And we will have, but it might, yeah, but we might predict more values than there are labels. For example, we can, if the labels are binary, 0 and 1, we can choose 0.5. And the loss will be, we will take things simple. We will take absolute value of our labels and the predicted label. Our label and the true, I mean, the given label by the opponent. So all results will hold for loss function that is convex in first argument, but let's keep things simple. Okay, so here is formal definition of game. So there is, the labels are called outcome space, there is action space. And then we assume we have more actions than labels, everything natural numbers. We have, the game depends on number of experts. And for some results, we fix the number of rounds. Okay. And then the rounds are, so we first receive all predictions, then we make a forecast, and then we get the true label. And then the losses are defined. And so there are two types of losses, our loss and the loss of the experts. And so the goal is to predict as well as the best expert. So the difference is called regret. Okay. And so there is a first observation that if our action space or decision space is equal to the labels equal to binary interval, then environment, so those who controls predict the experts and the true labels, he has a strategy to make us lose, to have regret at least half of the rounds. So maximal regret we can have is number of rounds if we lose one in each round. So if we predict always wrong, we have half, our loss is T. And in principle, we can have regret T. If we do something really stupid, If there are, for example, two experts who always say 0 and we always say 1, then we have regret T, but it's not possible to have more. But environments or our opponent has always a strategy to make us have regret at least T over 1/2. And you, in the previous seminar, you discussed about it. But if we increase the decision space, then we can get something better. So now let us have decision space. I wrote 0, 1 interval, but let's say 0, just 3 numbers, 0, 1, and 1/2, but still binary labels 0 and 1. So then we can decrease the regret from T over 1/2 to T over 1/4. So we have a strategy to have regret at most T 1/4 of T. And this strategy is called follow the leader. So so what's the plan is that imagine we have so there is a strategy to have T over 4 if there are two experts. Yes. Yeah, we can predict 1/2, and then the loss we receive is always 1/2 because either the label is 0 or 1, and in both cases, absolute difference is, yeah. And so the plan is that sometimes we prefer to have certain loss 1/2 instead of uncertain loss 0 or 1 in order to play against the worst case opponent. Okay, so this is a game. And then the question is, what is the minimal regret we can enforce in this game? So it's very similar to agnostic setting in mistake bound, except that we don't have a set of classifiers and we don't have inputs. But we have a bigger decision space. Okay, so let's have 3 values here. And so the plan is that if experts agree, we say the same. And if they disagree, we follow the expert with the biggest, with the smallest loss. Let's follow the leader. Okay. And then they claim that we have, but if there is a tie between the experts, then we go for certain small loss. So we will say 1/2. That's the only case. And now the claim is that in every round with even index, so every even around 7, 4, and so on, we make at most T over 2 mistakes. The loss is at most T over 2. The regret is at most, sorry, I said again, regret is at most T over 2. Okay, well, why is it? So yes, we only need to look at rounds where we make a mistake. So if this is if these are rounds where we're following the leader, then we are good because the best so the regret is difference between our loss and predictor's loss, a best predictor's loss. So, okay, maybe I didn't stress enough. Yeah, so to predict as well as best predictor. So if we make a mistake and we're following the leader, then it means that our regret doesn't increase in this round because our loss increases and the best predictor's loss also increases. We are good. And so the only way that our loss can increase is if there is a tie between the two predictors. But then our loss increases only by 1/2. But we can think in any 2 consecutive rounds, can we have 2 times a loss 1/2? No, indeed, because experts can only disagree and have a tie in one of the 2 rounds. The one who is right will become the leader, and then we have a leader and we are good. Okay, so this is thing. And so now let's consider randomized weighted algorithm. So now what we do, it's difficult to see in the room. So we take continuous decision space, and then we can get, instead of linear regret t over 4, we can have a square root t regret if there are not too many experts. Okay, and so we will get the strategy by tuning some parameter alpha and proving a bound that depends on alpha. Our proof will work for alpha bounded by 1/2, alpha at most 1/2. Oh, sorry, this doesn't need to be strict inequality on the top. There is a small mistake. In the notes, it's correct. Okay. So if alpha is bigger than 1/2, then from this bound, we get the theorem immediately. And otherwise, we set alpha to the optimal value, and we also get the theorem. Okay, so let me say why we get for big alpha. Sorry, sorry, I'm not saying right. So there are two. Okay, so first let us optimize this inequality. We get the alpha that's written the root of ln n divided by t. Okay, if this root is smaller than 1/2, at most 1/2, then we get the result of the theorem. And if this root is bigger than 1/2, then in the last two lines, you see it, t bounded by 4 ln n. That means alpha bigger than 1/2. But then, okay, let's multiply this condition by t on both sides and take square root. So then we have this thing, t bounded by square root t 4 ln n. And now let us compare this to the theorem. We see that the regret in round t is always at most t, regardless of the strategy. So in this case, we're also covered. So the only thing that we need to do is assume alpha at most 1/2 and prove the bound in the middle of the slide. Okay, and this actually goes with very familiar algorithm. So before we always predicted majority vote or weighted majority, but now we can have more values. We can values between 0 and 1, so we will just take this weighted average. And those predictors, so those experts who are right, that we keep their weight, and the other ones, we decrease their weight. And now it just follows, the proof follows the technique before, but we will use one substitution. So we will use that absolute difference between experts and true our prediction and correct label is equal to the weight of all experts that were false. So you can just think about the two cases and look to the formula and the prediction. And so each time the weight of predictors that predict wrong pushes this y to away from the correct answer. Okay, so that's bottom we need to remember. And then we can do precisely the same thing that we did already many times in the first lecture. So let us look to how the total weight updates at the next round. So let's look to the second line. First line is just remembering what we need to prove. Okay, so let LT be our loss in the Tth round, and it's precisely weight of experts that are wrong. We know that these weights get multiplied by 1 minus alpha. So this is the first term. The first term is weights of predictors that make a mistake. The second term is the weight of normalized weight of other predictors, which is 1 minus L. So then there's just some linear algebra, and then we use exponential bound. So it will be used all the time, of course. 1 plus r is smaller than exponent r. for all real numbers, right? So, okay, so we know how the ratio of weights updates in each round. So now we look to all of the updates and then look to the weights of best expert and say that the weight of the best expert is at least the total weight at the end of the game. In the beginning, oh, I forgot to tell, but the beginning all weights are 1. So then this gives us the formula in the middle. It's the same thing. You already did 3 times. So this is the 3rd time. And then, or 4, okay, doesn't matter. Then we take logarithms. And then in the end, we have to use some annoying inequality. So you can prove it just by writing it exponent. And then you need two Taylor terms from exponent. And so it's the same like this, but like this. And R will be plus 6. Just some linear algebra to get this thing. But you need to assume that alpha. You need here you need to use to get this inequality, you need alpha at most 1 half. For 1 half. Okay. So yes. Okay. Now let me quickly go over 2 results that will be important in the rest of the course, and then exponentially weighted average you need to do yourself. But I prepared quiz, so you need to fill in quiz, and you get 0.1% on final score. So let me just talk 4 minutes more, and then so that I can do the quiz. Otherwise, I prepared for nothing. Okay, so Jensen inequality, you already learned this. Okay, then maybe I can skip it. No, okay. So there is your weight is average, your length is average, and it might mean that you're too fat. Yeah, Jens. Oh, sorry, Jensen inequality. Okay, yeah. But it's kind of cool. So I have found about nurse sharks. They have like really humans. It's very noisy, and so nurse shark has cubic regression, and so the average weight and average length is a shark that's clearly overweight. And so if it's linear, we take expectations, and then expectations of f is more than f of expectation, and so on. Okay. Second thing is Hoeffding's lemma. So when we apply Jensen inequality, exponent is convex function, we have this inequality. But what if we need the other inequality? This is needed for exponentially weighted algorithm. And so there is Hoeffding lemma, which is on the bottom. Can be used for other side of inequality. And so there is eta. So you can just set eta equal to 1, for example, and get this thing. And actually, this is like horrible proof if you want this 1/8 in the coefficient. But if you're happy with coefficient 1, then it's kind of easy proof because it follows from a Taylor approximation of exponent. And so what's happening here, it will just be the second Taylor term of exponent. So yeah, so the proof you see in the bottom. If you want. Okay, this is all what you need to know for seminar. But then this nice proof of exponentially weighted algorithm, you will need to learn yourself. And lower bound is just optional. The slides are there, but it's a bit village inequality you need to know for this. And there is like really cool proof invented by YouTuber. So I was on YouTube, suddenly there was this amazing proof. So I've been searching for a nice proof because of this course, and then YouTube gave it to me. So it's one blue tree brown. Maybe you know, yeah, it's like really impressive movies. And yeah, this was really cool. Okay, so let's finish here and see you next week.